Okay, now I want to talk about second order linear differential equations, except that I will now start to consider the case where the coefficients in the linear differential equation are not constants. They can be functions of x. Okay, they cannot be functions of y, because then of course you don't have a linear equation. Okay, so you are dealing with equations of this form. So you're dealing with now equations of the form given here and here. Okay, so a1 and a0 now can be functions of x. Okay, right. Before doing this, let me first of all discuss how do you solve the non-homogeneous equation in general. Okay, so essentially you first of all, as we have seen, you focus on the homogeneous equation. Okay, so the idea being, and I'll show you now, the idea being that if you know the complementary function, as in if you know the solution to the homogeneous differential equation, this one, then you can figure out the solution to the non-homogeneous equation, this one. Okay, I'll show you why that is true. So there are two ways to go about it. First of all, suppose that you know the part of the complementary function. Remember, for the second order linear differential equation, the complementary function consists of two independent functions. Okay, so the complementary function is a linear superposition of two independent functions. Okay, let's call one of those functions u of x. Okay, the idea then is that you make this substitution. Okay, when you do this substitution, when you substitute this back into your differential equation, actually when you differentiate this back into the original differential equation, okay, you get, instead of a differential equation for y, you get a differential equation for v. Okay, and it turns out that the differential equation for v, okay, you get a first order differential equation for dv by dx. Okay, and you know how to solve a first order differential equation. Okay, they are more technique. It's easier to solve a first order differential equation for dv by dx. Okay, so once you have that, then you integrate that to find out v of x. Okay, and once you have v of x, then of course you have y. Okay, okay, now it's easy to show how that works out in practice. Suppose you have this equation. Sorry, suppose you have this equation, right? Okay, now there's a non-homogeneous term. Okay, so you don't, this is a non-homogeneous differential equation. Okay, but first of all, the idea is that first of all you find out the complementary function. So to find out the complementary function, you need to solve this differential equation, and we know how to solve this differential equation. The solution is straightforward. This is simply the undamped, unforced, simple harmonic oscillator equation. So we write the solution has to be of this form. Okay, now like I said before, if you know part of the complementary function, okay, then you can figure out the rest of the complementary function as well as the particular integral. Okay, at least in principle. Okay, so let's say that you say, okay, you said u is equal to cosine of x. So you say, okay, I know part of the complementary function. Forget about this constant. You know a part of the complementary function, so I set u is equal to cosine x, and then I say that y is equal to uv, which is equal to cosine of x times v. Okay, so this is going to be my substitution in this differential equation, and this one. Okay, and what I'll then get, as I'll show you, is a differential equation for dv by dx. So using this thing, let's first of all find dy by dx. So dy by dx, it turns out, is you just use the product rule. So you have v minus sine x plus cosine x dv by dx. Okay, but you don't need the first derivative of y, you need the second derivative of y. So you plug that in. So the second derivative of y is going to, you differentiate dy by dx. So again apply the product rule. So v you take outside, minus sine x, the derivative of that is minus cosine x, then you have minus sine x, and then you have dv by dx, right? And then you have cosine x, and then you have double derivative of v, and then you have plus dv by dx minus sine x. Okay, so in all these detailed methods, it seems along the way that you're getting a bigger mess, but have hope. Okay, it simplifies usually. So what you then get is that the second derivative is going to be equal to cosine of x, double derivative of v with respect to x, minus 2 sine x dv by dx minus v cosine of x. Okay, right? Fine, and now you plug this back into your differential equation, this one. Okay, so you have over here then cosine of x, double derivative of v with respect to x, minus 2 sine of x dv by dx minus v cosine of x, right? This is the double derivative of y, and then you have to plus y, and y, remember, is v cosine x. So you have v cosine x, right? That's your simplification. This time cancels that term, right? And this whole thing is of course equal to cosecant x. Okay, right? So this is, remember, is a nice substitution to have. Okay, because essentially you don't know how to find out the particular integral for this differential equation using the techniques that we have done until now, because this right hand side is not something that looks like an exponential. It's not a simple sine or cosine. It's not a polynomial multiplied by an exponential. Okay, so it's not a polynomial either, so you don't really know how to find out the particular integral. Okay, but now you at least have something in your arsenal that allows you to do so. So, and the left hand side now is simply cosine of x, double derivative of v, minus 2 sine x dv by dx is equal to cosecant of x. Okay, and now you can divide throughout by cosine x, right? So you'll get essentially that this thing is equal to, okay, minus 2 tangent of x dv by dx is equal to cosecant is 1 over sine of x, and 1 over sine of x, and then you're dividing by cosine of x, so this is going to give you cosecant of x secant of x. That's essentially what you get. So then you can actually make a substitution that z is equal to dv by dx, right? Or just so that you have w is equal to dv by dx, and then you can write now your second order differential equation is actually a first order differential equation in w. Okay, so dw by dx minus 2 tangent of x, right? W is equal to cosecant x secant x. So this is a linear first order differential equation which you know how to solve. So you solve that and you will get w, right? And then you, once you have w, you can integrate this equation on both sides. So you integrate w with respect to x to get v. Okay, and once you have v, of course, then you have y. Remember, y is equal to uv, and you already know u. Okay, right? And of course you are doing two integrations essentially. So you're doing, when you solve this differential equation, you'll get one constant. When you solve this differential equation, you'll get another constant. So of course your solution will contain two constants. It will also include the particular integral. Okay, because remember you have something non-zero on the right hand side. I leave you to fill up the details. Okay, so what you will get is essentially what you should get after the integration and all. I'm not doing it because I'll be solving exactly the same differential equation in another way very shortly. Okay, so what you should get is c1 sin x plus c2 cosine of x. No surprise there, right? Because that's just a complementary function. Okay, this one. And then the rest of it is of course a particular integral, which comes out to be, once you have done the integration, okay, the integration is not that trivial, okay, which is why I am not doing it. Okay, ln sin x minus x cosine x, okay, but you should be able to do the integral. Okay, so this is the particular integral, and this is of course the complementary function. That's your whole y. Okay, right. Fine. This technique is especially useful. Okay, this technique of knowing the complementary function is also useful for finding out the other part of the complementary function. Okay, so for example, over here, all I used was the fact that u is equal to cosine x. I could have used u is equal to sine x equally well as well. So suppose I guess from the equation that the solution for the homogeneous linear differential equation, this one solution is u is equal to cosine x. Then just by using that, I can figure out automatically what I found was that sine x is also a solution. Okay, so in many cases, this equation that you begin with is a homogeneous equation. Okay, so just by looking at, you can guess a function which solves that homogeneous function equation. Okay, but of course that's not the complete solution, because you need another independent function that also solves that homogeneous equation. Okay, and guessing the second one might be not easy. Okay, it might not be easy. Okay, so you can use this method to actually figure out what the other independent function is that also solves the homogeneous linear differential equation. Let me give you a simple example. Okay, so you have this differential equation. Now you see the coefficients are functions of x. Okay, minus 2x dy by dx, right, plus 2y is equal to 0. Okay, you might be saying that this does not look like the form that I wrote down in the beginning. Okay, this one, but all you need to do is of course divide both sides of this equation by 1 minus x square. The right hand side is 0 for the equation I've written down, so the right hand side remains 0, but then you have this coefficient becomes 2x over 1 minus x square, and this thing becomes 2 over 1 minus x square. Okay, so that's what you have. Now it's easy to just look at this equation. Okay, it might not be easy to you, okay, but with some enough experience and practice, you can guess that this function, a very simple function, probably one of the simplest functions you can possibly imagine, solves this differential equation. Why? Because the double derivative, of course, of y with y is equal to x is of course 0. Okay, the single derivative is of course 1. Okay, so this first term goes to 0, the second term is of course becomes equal to minus 2x, and of course with y is equal to x you get plus 2x over here, so of course y is equal to x is a solution. Y is equal to some constant multiplied by x is also a solution. Okay, so that's a given because you're dealing with a linear differential equation. Okay, so this is part of the complementary function. Okay, what's the other part? It's very difficult to actually guess that. It's impossible to guess that actually. Okay, but you can do this thing. Y is equal to u multiplied by v. So you set u is equal to x. Okay, so then this implies that you use a substitution, y is equal to vx. Okay, plug this back exactly as we did before into this differential equation. Work out the second derivative, work out the first derivative, substitute all this, and then you'll get a linear differential equation for dv by dx. Okay, that's a first order equation for dv by dx. Solve that first order differential equation to find dv by dx, integrate that to find v. Okay, and once you have v, multiply v by x to actually find out the full the full complementary function. Okay, and what you find is that the full complementary function is y is equal to c1x plus c2 x by 2. Again, I leave the integrations for you to do, divided by 1 minus x minus 1. That's what you have. Okay, so as you can see, the other part of the complementary function is very complicated. There is no way that you could have guessed that. Okay, it actually contains a logarithm. Okay, right? Fine. Okay, Now there's another method to find out the particular integral. Okay, remember this method that we have just discussed allows you to find out the full complementary function as well as a particular integral, provided that you know only part of the complementary function. The second method, okay, works in the case where you can very easily find out the full complementary function, which was of course the case for this equation, because we could very easily find out the full complementary function. Once you have the full complementary function, then this second method, which is known as the variation of parameters method, allows you to very quickly, very efficiently find out the particular integral. Okay, but it relies on the fact that you know the full complementary function, not just part of it. Okay, so the variation of parameters method works when you know the full complementary function. YC allows, and then this allows you to find the particular integral. Okay, let's see how this works out. So we know that the complementary function is of the form c1y1 plus c2y2, because you're dealing with the linear. Remember, you're always dealing with the linear differential equation over here. That is not to say that non-linear equations never pop up in physical applications. They do, okay, but by and large it's very difficult to solve them. Most of the time you just solve them numerically. Okay, right? Okay, so you know yc is of this form. Okay, variation of parameter says that essentially you promote these constants to functions of x. Okay, and then you hunt around for functions of x such that the differential equation is solved. Okay, so it's very similar to what we did before for first order linear differential equations. Remember how we found out the solution to those? We first of all said, okay, dy by dx plus p, where p is a function of x, y is equal to q of x. We first of all said, okay, let's find out the solution for the homogeneous equation. And then we said, okay, the solution to this is c e raised to power minus I, right, where I is given by the antiderivative of p. And then we promoted this c to a constant. This constant c to a function of x. Okay. And once you promote this to be a function of x, then you plug this back into this differential equation. And then you found exactly what c is going to be. Okay, right? So essentially that was variation of parameters for a first order differential equation. But now we will generalize the method to a second order differential equation. Okay, so it works like this essentially. So what you have is that your particular integral is of the form c1y1 plus c2y2. But now keep in mind that c1, y1, c2 and y2, all four of them are functions of x. Okay, so what you have then is essentially that you the differential equation that you have to solve is this thing, a1 y is equal to some non-homogeneous term, right? Okay, right. Then what? Then you have to essentially work out dy by dx. Okay, so I'm assuming that my y is of this form, because I'm working out the particular integral. So I'll just write that y is of this form, c1y1 plus c2y2. Okay, right. So I'll first have to work out dy by dx. So you have c1 dy1 by dx. Just use the product rule, remember, because c1 and c2 are not constants. So you have y1 dc1 by dx plus c2 dy2 by dx plus y2 dc2 by dx. Okay, I also need to work out the second derivative. Okay, but before doing that, stop. Okay, and look at this. Okay, so you essentially have that you have over here dc1 by dx this time plus this time, right? Okay, and you can group these terms. So you have over here this thing and this time. You have y1 dc1 by dx plus y2 dc2 by dx. Okay. Now c1 and c2 of course are some functions of x. Okay. There is no constraint on them except that the y that I get by constructing this needs to satisfy the differential equation, and that's exactly how I'm requiring that condition to be satisfied. That's why I'm substituting dy by dx and later on the double derivative of y into of x, double derivative of y with respect to x into this differential equation. So I'm substituting this form of y into this differential equation. That's exactly what is going to enforce the fact that y is going to satisfy the differential equation. So that's one constraint. I can also impose another constraint on my on this. In particular, I can impose a constraint of c1 and c2. Okay, as in I can impose the constraint that this thing in the square brackets is equal to 0. I'm just doing that just to simplify my life. Okay, because otherwise your dy by dx is coming out to be a complicated mess, and you can immediately see then that the double derivative of y is going to be an even more complicated mess then. Okay, but because I have some freedom in choosing my c1 and c2. Okay, right? Yes, there is a constraint that c1 and c2 have to be such that this differential equation has to be satisfied, but other than that there is no constraint whatsoever. Okay, so hopefully I can impose another constraint and still be able to find c1 and c2 such that both these constraints are satisfied. Okay, right? So just for notation simplicity, I use a prime to denote a derivative. So I have imposed this condition. So let's call this that this is my equation 1. Okay. With this, you see the whole point of doing this was that the derivative simplifies. So you have c1 dy1 by dx plus c2 dy2 by dx. Okay, and then this immediately implies that the double derivative of y with respect to x is going to be c1 d2y by dx2 plus dy1 by dx dc1 by dx, right? And then a similar game for the second term. Right? Okay, so far so good. Now I just substitute these derivatives into my differential equation, which is exactly what allows me to impose a condition that the differential equation is satisfied. Okay, so you have c1. So again, you'll be saying, oh, this is becoming a big mess. Okay, hang on. Okay, oh sorry, this is y1. Okay, y1 plus dy1 by dx dc1 by dx plus c2 d2y by dx, this is y2, right, plus dy2 by dx dc2 by dx, plus I remember I also have the first derivative over here, but I also have to make sure that I multiply everything with a1. So you have plus a1 c1 dy1 by dx plus c2 dy2 by dx, and then you have a0 multiplied by y, and y remember is c1 y1 plus c2 y2, and this equals 0. Oh sorry, not 0, this equals f of x, right? Fine, this is a horrible mess. Okay, but it's not that horrible. Okay, because you can group terms that contain y1 and you can group terms that contain y2. Okay, so let's let's group terms that, let's group terms that contain only C1, and let's group terms that contain only C2. Not derivative of C1, not derivative of C2. Okay, that's actually what leads to the simplification. So you have C1 double derivative of y1 by dx2. Okay, that is this term. Okay, plus you have over here, forget about the second term, you have over here a1 dy1 over dx. Okay, plus you have then a naught y1. So you have done this term and this term. Then you do the same game with C2. So C2 double derivative of y2 plus a1 dy2 by dx plus a naught y2. This term and this term. Okay, right, and of course this term. Right, you're left with the two terms. This term and this term are left. Okay, right, so you have then plus dy1 by dx dc1 by dx plus dy2 by dx dc2 by dx is equal to f of x. And now something magical happens. This thing in the square bracket is equal to 0. This thing in the square bracket is also equal to 0. That's simply because y1, remember, go back. What was y1? y1, remember, was a solution to your homogeneous second order linear differential equation. y2 was also a solution to your homogeneous second order linear differential equation. That's why the superposition of them is your complementary function, general complementary function. Okay, and the fact that y1 is a solution to your homogeneous differential equation means that this thing in the square brackets has to be equal to 0. That's exactly the definition of how you find out the complementary function. And the fact that y2 is also a solution of your homogeneous linear differential equation, that means that this thing is also equal to 0. So you are simply left with the second line, namely that, again I introduced the notation, the prime for the derivative. You have simply that c1 prime dy1 by dx plus c2 prime dy2 by dx is equal to f of x. Okay, right. Of course you know y1, you know y2, right, because you know the complementary function. And then you, of course, you know the derivatives as well. So you know dy1 by dx and you know dy2 by dx. Okay, so this is your equation 2. Right, so if you look at equation 1 and equation 2, you have two simultaneous equations for c1 prime and c2 prime. Remember, you have to find c1 and c2, right? Because if you know c1 and c2, then you know y, because you know y1 and y2. Right? If you know these two, you know y. Okay, fine. So you have two equations that you have to solve simultaneously. So c1 prime and c2 prime, equation 1 and equation 2. I can recast those equations in terms of matrix equations. Okay, so you have y1, y2, y1 prime, y2 prime. Then you have c1 prime, c2 prime. Right? Oops, this became a little bit too big. C1 prime, and this is equal to 0 f of x. Right? So to find c1 prime and c2 prime, it's very easy to do that. Right? You just take the inverse of this matrix. Okay, and then you multiply this matrix equation on both sides with the inverse of this matrix. Okay, and then you have c1 prime and c2 prime. Once you have c1 prime and c2 prime, you integrate those equations, okay, to find c1 and c2 and plug that back into y, into c1 y1 plus c2 y2, and then you have your full solution. Okay, let me show you how that works out in practice. Okay, so again, let's look at this differential equation. right? So we know the complementary function to this differential equation, that's just c1 cosine x plus let me use a sine x instead, sine x plus c2 cosine x. That's your complementary function. Okay, so what the variation of perimeter does is, of course, promote the c1 and c2 to be functions of x. Okay, and then you essentially have the same derivation as we did before until you reach this step. So remember that this is identified as your y1, this is your y2. Okay, so you have this matrix equation for c1 prime and c2 prime. So you have sine of x, you have cosine of x, you have derivative of y1 which is cosine of x, you have derivative of cosine of x which is minus sine of x. This multiplied by c1 prime, c2 prime is going to give you 0 and cosecant x, because f of x is of course cosecant x. That's that. Okay, so the inverse of this matrix, of course, to find out the inverse of this matrix, you find out the determinant of this matrix. The determinant of this matrix, by the way, if you look at this if you look at this matrix, the determinant of this matrix is just a Wronskian. Okay, and essentially the determinant of this matrix in this case is minus sine square x minus cosine square x, right? And that of course is minus 1. Okay, so you have that c1 prime, c2 prime is given by 1 over determinant of this matrix. You get 1 over minus 1, and then you have to swap the diagonals and then tack on a minus sign onto the off diagonals to find the inverse. Right, and so you are going to get essentially that you have sine of x, cosine of x, cosine of x minus sine of x, 0 cosecant x. And so you can read off the c1 prime is going to be equal to cotangent x, right? Fine, because cosine x multiplied by cosecant x is cosine x over sine x, which is cotangent x. And you have c2 prime is going to be equal to minus sine x multiplied by cosecant x, which is going to be minus 1. Okay, so you can now integrate both of these equations to find c1 and c2. c1 of course is going to be ln of sine of x. Okay, right, because you have cotangent x is cosine x over sine x, the derivative of sine x is cosine x, and that's already in the numerator. And c2 prime is equal to minus x. Okay, so in other words, you have that the particular integral is going to be given by, just plug these over here. Okay, so you have sine x ln of sine x minus x cosine of x, right? Fine, so that's essentially what you have. Okay, you might be of course be wondering where the constants of integration disappeared. Okay, I'm finding out the particular integral, so I'm disregarding any constants of integration that appear. If you want, you can plug in the constants, but those constants are going to combine with the constants in the complementary function to give you new constants. You can try that if you want. Okay. Okay, now I come to the main part of this lecture, which is to solve second order linear differential equations with coefficients which can be functions of x. Okay, so essentially you're dealing with equations of this form. So you have a1 dy by dx plus a naught y is equal to, treating it equals to 0, so I'm looking at the homogeneous equation. Okay, it might be that the actual equation that you're interested in is of this form. Okay, even if it is not, so that the right hand side is non-zero, but as long as it's a function of x, then we can deal with that. Okay, first of all we find out the complementary function, and then from that we can construct the particular integral that we've seen before. Okay, so by and large I'll be interested in equations of this form, but now remember that a0 and a1 are functions of x. Okay, the favorite way to deal with such a differential equation is to assume a series solution for y. Okay, so essentially what you say is that you assume that y is of this form. Okay, so essentially y is a polynomial series. Okay, fine. The idea then is, of course, to figure out these coefficients in this possibly infinite series expansion. Okay, fine. Okay, so let me show you how it works. Okay, in principle, it's just easiest to just show the method by demonstration. Okay, so let's take a differential equation which you already know how to solve. Okay, so essentially let's consider this differential equation, probably the simplest one that you have. So this is a nice simple harmonic motion differential equation. Okay, and I'll assume that y, again I'll assume a series solution for y. Okay, right. So the trick now is to use this series, assume such a solution. Okay, and we'll discuss later when such a solution can exist. Okay, you assume such a solution and plug that into your differential equation. So first of all I have to work out the derivative of y with respect to x, assuming such a series solution. And since the derivative is linear, okay, the derivative operation you can take inside the sum. A and are constants. Okay, and comes down by the power root for differentiation n raised to power n minus 1. Okay, right, fine. So that's what you have. Notice that this series begins with a constant term because x raised to power 0 is 1, and you have plus a1x plus a2x square, so on. So it's obvious that the derivative of y will begin from a1. Okay, and that's exactly what you're seeing from here. Remember, when n is equal to 0 you get 0. Okay, for this, because you have an multiplied by n multiplied by x raised to power n minus 1. Okay, so I might as well start this series from n is equal to 1, right, because the n is equal to 0 time is 0 anyway. Okay, right. Then I can take the double derivative. Okay, and when I take the double derivative I have n is equal to 0 to infinity. Let's just take this form of the first derivative. You have n, and then by the power rule n minus 1 comes down, and you're left with x raised to power n minus 2. Okay, notice now that in this term the n is equal to 0 term is 0. In this sum the n is equal to 0 term is 0, and the n is equal to 1 term is also 0. That's expected, because given the form of y, the first derivative starts from a1, right, and then the second derivative starts from a2. Okay, so that's why you have the n is equal to 0 term is 0, and n is equal to 1 term is also 0. Okay, so we might as well start from n is equal to 2. Okay. You'll see later on why I'm doing these manipulations, that why I'm saying that you can start from n is equal to 2, or why we can start from n is equal to 1. Okay, so you have n times n minus 1 x raised to power n minus 2. Okay, so you plug this. Let's just plug this into your differential equation, this one. Okay, and then you plug this thing over here, right? So the double derivative of y with respect to x is, of course, n is equal to 0 to infinity a n times n minus 1 x raised to power n minus 2, plus you have over here y. Okay, so you have plus n is equal to 0 to infinity a n x raised to power n is equal to 0. So the idea over here is to combine the sums into a single sum. Okay, right, but that's not so easy to do over here, because you have x raised to power n minus 2 over here and x raised to power n over here. Okay, what I can do, of course, is to bring about x raised to power n over here as well. Okay, so to do that, I realize that n is the mean index. Okay, so first of all I say that, okay, n raised to power 0 to infinity a n minus 1 x raised to power n minus 1 2. I can, instead of n, I might as well use L or M or P or Q or whatever your favorite alphabet is. It's not going to change the result, okay, because the index of summation is always a dummy index. So for example, I is equal to 1 to 3 of AI is equal to J is equal to 1 to 3 of AJ. It doesn't matter what I use as the index over here. The left hand side is A1 plus A2 plus A3. The right hand side is A1 plus A2 plus A3. Okay. So I might as well use some other index over here instead of n. Let's use another index, n prime, which I define as n minus 2. Okay. Now, if n is equal to 0, then it's obvious that n prime is going to be equal to, when n is equal to 0, n prime is going to equal to minus 2. Okay. But, well, what do you get then? Okay. If n prime is equal to minus 2, so you don't get something that neat, okay. But you also realize that you can write this thing as n is equal to 2 to infinity a n minus 1 x raised to power n minus 2, because remember the n is equal to 0 term and n is equal to 1 term are 0 anyway, okay, in this sum. Right, okay, and now you make the substitution in this sum. That's why I was emphasizing that you can write this double derivative as this sum. Okay, now you make the substitution, right? Then what do you get? So you first of all have to change the limits of summation. Changing the limits of summation when you go from one index to another index is very similar to how you change your limits of integration. Okay, so when n is equal to 2, n prime is equal to 0. So you write n prime is equal to 0. When n is equal to infinity, then n prime is also infinity. So you get that. Then you have a, and instead of n, I have n prime plus 2, because remember, if n prime is equal to n minus 2, then n is equal to n prime plus 2. Okay. So instead of n, I have n prime plus 2, and then n minus 1 is n prime plus 1, and then you have x raised to power n prime. So that's an equivalent way, entirely equivalent way of writing down the double derivative of y. Okay, but now since you have your n prime is a dummy variable, I might as well just call it anything. Okay, and I've done I've massaged the sum into a form that I want. Okay, because I want the form to be containing x raised to power n. Okay, so I might as well just call it n again. Okay, so this is so this is just a n plus 2, n plus 2, n plus 1, x raised to power. Effectively, I just remove the prime. Okay. Right. So then going back to a differential equation, right? This then implies that you have n is equal to 0 to infinity a n plus 2, n plus 2, n plus 1, x raised to power n plus n is equal to 0 to infinity a n x raised to power n is equal to 0. Okay, and then I can write this left hand side as a single sum. So I have a n plus 2, n plus 2, n plus 1 plus a n, right, x raised to power n is equal to 0. Okay, since this equation has to hold true for every x, the only way that this can hold true is if this thing in the scale brackets is equal to 0. So immediately write down that a n plus 2, n plus 2, n plus 1 is equal to minus a n. So I have that a n plus 2 is equal to minus of a n divided by n plus 1, n plus 2. Okay, that's what I have. This is something called the recursion relation. This allows you to find the coefficients in your polynomial expansion, provided that you have the value of one coefficient. Okay, you can call that the seed of your polynomial expansion. Okay. Now notice something. If you have a0, if you have a0, remember your series expansion y. Let me just write it again. if you have a naught, which is the constant term in this polynomial expansion, then you can generate from this recursion relation, that's what it is called. Okay, you can generate from this recursion relation a2, a4, a6, a8 and so on. Okay, but you cannot generate the odd power, the odd terms. Okay, you cannot generate a1, a3, a5. For those you need to specify the value of a1. If you have specified the value of a1, then of course you can get the value of a3, a5, a7 and so on. Okay, so you have two independent constants that you need to specify, a0 and a1. Okay, a0 generates all the other even coefficients, and a1 generates all the other odd coefficients, and that's to be expected because you're dealing with a second order differential equation, so you need to have two undefined constants in your general solution. Okay, right, fine. So let's now play around with this. So suppose I have a0, then from this I can figure out a2. So I just use the above recursion relation. So I have minus a0 over, and I have n is equal to 0 over here. So I have 1 over here, and I have 2 over here. So this is minus a0 over 2. Similarly, a4 is equal to minus a2 divided by, and n is equal to 2 over here. So I have 3 and then 4 over here. Okay, and this by substitution is because a2 is minus a0 over 2. This is equal to plus a0 over 4, 3, 2. So a pattern is emerging. So I might as well just write this as a0 over 2 factorial. I might as well just write this as plus a0 over 4 factorial. Okay. a6 is given by, using the above relation, the recursion relation is given by minus a4 divided by n is equal to 4, remember. So you have 5 and then 6. So you have minus, and a4, remember, is plus a0 over 4 factorial. So you have minus a0 over 6, 5, 4 factorial, which is simply minus a0 over 6 factorial, right? So going on, you can kind of see the pattern already. Okay, so a8 will be equal to plus a0 over 8 factorial and so on. Okay, right, fine. Okay, and similarly, if I start from a1, right, then I can write down from this a3 is going to be given by minus a1 over, just using this recursion relation, and you remember n is equal to 1. So you have 1 plus 1 is equal to 2, and 1 plus 2 is equal to 3. So you have 2 and then 3, which I just write as minus a1 over 3 factorial. And then I can write a5 as minus a3 divided by, what do you have? You have essentially you have over here n is equal to 3 over here. So you have n plus 1 4, n plus 2 5, 4 and then 5, and then of course this is a1 over 5 factorial. Okay, and so on and so forth. Okay, so the general solution, remember, was y is equal to n is equal to 0 to infinity e n x raised to power n. So this is a0, and then you have plus a1 x plus a2 x square, but a2, remember, is minus a0 over 2 factorial x square, right, plus a3 x cube, but a3, remember, is a3 is minus a1 over 3 factorial x cube plus a4, and a4 is plus a0 over 4 factorial x raised to power 4. Okay, plus a5, which is a1 over 5 factorial x raised to power 5, right? Okay, and plus a6, which is minus a0 over 6 factorial x raised to power 6, and so on. Okay. I can group the terms that contain the even powers of x. Okay. So, and of course all the even powers of x have this a naught in them. Okay, so I can factor out a naught, and then I have 1 minus x square over 2 factorial plus x raised to power 4 over 4 factorial minus x raised to power 6 over 6 factorial plus blah 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 plus a1, right? And you have over here x, right, minus x cube over 3 factorial, right? And then you have plus x raised to power 5 over 5 factorial minus blah blah blah. Okay. The term in the first square brackets you recognize as the power series expansion of cosine of x. The term in the second square brackets you recognize as the power series expansion of sine of x. So I can write this as this. Of course, okay. You have reproduced the solution to the differential equation, the harmonic oscillator differential equation, by assuming a power series expansion. Okay. The key, remember, is first of all assume such a power series expansion, plug it back into your differential equation, and then figure out the recursion relation. Form the recursion relation. You build up your power series. Okay, right? Okay. Before going on, let me just be clear, okay, about some manipulation of the sum that we did before. You looked at essentially, you assumed y is equal to 0 to n x raised to power n, and we worked out that dy by dx is equal to n is equal to 0 an n x raised to power n minus 1, and then similarly the double derivative is given as an n minus 1 x raised to power n minus 2. Okay, fine. At this step you can already include do the variable substitution, so you can say that okay, n prime is equal to n minus 2. So when n is equal to 0 you have n prime is equal to minus 2. Okay, and when n is equal to infinity, n prime is of course infinity. Okay, so you have a, and then you have n prime plus 2, and then instead of n you have n prime plus 2, and then you have n prime plus 1 x, n prime plus 1 and x raised to power n prime. Okay, now this and then of course you have to combine this with y, right? They almost look the same, except that the sum over here is from 0 to infinity. The sum over here is from n prime is equal to minus 2 to infinity. Okay, but you could recognize that the time corresponding to n prime is equal to minus 2 is 0 because of this thing, and the time corresponding to n prime is equal to minus 1 is 0 also as well because of this thing. So you might as well start this sum from 0. Okay, and of course you get exactly the same thing. Okay, and just to make this sum appear even closer to this sum, okay, you relabel the summation index in this first sum from n prime to n. Okay, so we have seen that if you have the differential equation and you assume a power series solution, you recover the usual sine and cosine solution. Okay, I can take this problem from the other end. Okay, I can say, okay, I can ask what do we mean with sine of x? What do we mean by cosine of x? Okay, so of course you say, okay, everybody knows what sine of x is. You just have a right angle triangle and you take essentially the ratio of the perpendicular to the hypotenuse. But suppose I want to go beyond right angle triangle. How do I define sine of x and cosine of x? Okay. One way is to do that, of course, is just write down the power series that, okay, here's the power series. It's convergent for all values of x. And once you have the power series of sine of x, that's how you can define sine of x. Once you have the power series for cosine of x, that's how you can define cosine of x. Okay, right? And that's exactly what we were doing over here. So we were identifying this power series by cosine of x. If you want, you can just say that, okay, cosine of x is actually shorthand for this power series. Okay, and sine of x is shorthand for this power series. Okay, I can actually give you another definition of cosine of x. I can say the cosine of x is the function which is a solution to this differential equation with some boundary conditions. Okay, the boundary conditions, of course, for cosine of x will be, yeah, this thing is true. Okay, and I also need another boundary condition. So let me just write down that the boundary condition, the derivative, of course, has to be equal to 0. Okay, for cosine of x. Okay, if I have this differential equation, right, and with these boundary conditions, then the solution, whatever solution I get, whatever the function I get as a solution to this differential equation, and that function satisfies these boundary conditions, I define that function to be cosine of x. Okay, you can take that as your definition of your cosine function. Okay, similarly, the sine of x function you can define as the solution to this differential equation, but with the boundary conditions these. Okay, you can easily check these claims, okay, because we have already solved this differential equation, right, and we found that essentially we solved this in the power series method. We have solved this using what we know already about sine of x and cosine of x. So let me just copy the solution as I wrote above. You have a naught cosine of x plus a1 sine of x. Okay, and if y of 0 is 1, right, then that implies that you put 0 over here, so you get essentially that a naught is given by 1. Okay, because cosine of 0 is 1. Okay, and you have y of y prime of 0 is going to be given by, well, the derivative of y with respect to x is a minus a naught sine of x plus a1 cosine of x, right? Okay, and then you essentially have that, okay, a naught is 1, so this goes away, and you need to figure out, and sine of 0 is of course 0, so this whole thing goes away, and x, we put x is equal to 0, so that's x is equal to 1, and this has to be equal to 0, so this implies that a1 is equal to 0. Okay, so essentially what you are saying that is that with these boundary conditions, the solution to the differential equation is simply cosine of x, as we claimed. Okay, so there's a whole collection of functions in mathematics, okay, which are defined, which you can define as solutions of some differential equations satisfying some boundary conditions. Okay, those are essentially common under the umbrella of so-called special functions, and there are many of these. Okay, so for example, you have Bessel functions. Okay, you have Legendre polynomials. Okay, you call them Legendre polynomials because these are finite polynomials rather than infinite polynomials. Okay, then you have Hermite polynomials. Okay, then you have Laguerre functions, and so on and so forth. Okay, all of these satisfy some second order linear differential equation which appears often in applied mathematics. Okay, and they satisfy some boundary conditions. Okay, because these differential equations appear so often in applied mathematics, okay, you just whenever you have such a differential equation, you just say, oh, I know the solution. Okay, it's a Bessel function if you're dealing with a Bessel differential equation. Okay, and then you have properties of the so-called Bessel functions tabulated. Okay, and there's some rules for manipulating them and so on and so forth. Okay, so you have to hold this dictionary of special functions. Okay, but that's where these come from. You cannot write them. You can think of in some aspect as that sine of x is not defined again in terms of a right angle triangle, but rather in terms of a power series. Okay, and once you know the power series, you can just say the sine of x is just shorthand notation for that power series. it's the same thing, for example, with the Bessel function. You can write down the Bessel function as something that looks similar to a polynomial expansion. It's not exactly polynomial expansion, it's slightly different for a Bessel function, okay? That it's something that looks like a polynomial series expansion, okay? And then you just say that, okay, Bessel function is just shorthand notation for the polynomial series expansion, okay? So that's where the whole field of special functions come in. So in the next video, I'll start by solving the so-called Gentry differential equation. I'll show you where the Legendre polynomials come from, okay, and then after that we'll be solving the Bessel differential equation and I'll be talking about the Bessel, okay. The rest of the special functions are very similar in spirit, so I'll be leaving those, okay, for you to do later on in your life whenever you have the time, okay, or whenever you actually have to do it because you encounter that particular differential equation that you actually need to solve is a differential equation such that the solutions are one of these special functions, okay.